Okay, and away we go. I sent everybody a email yesterday. You should have gotten the email. Just reminding you that I got the 7 and 8 homeworks up, and they will be due Monday when we get back. Not from Thanksgiving, but this weekend. So next Monday they will be due, and we're gonna have the 7 and 8 tests Monday. Um, We're already through with chapter 9. I went ahead and put the chapter 9 homework up. The chapter 10 homework is already up as well. So if you just like have some time and you're like, I'd like to get ahead on things, which some people like to do, they are up and ready for you. And we will have the chapter 9 and 10 test the Monday when we get back from Thanksgiving. So we're running a little bit short on time. Um, you know, you can work on stuff that Thanksgiving week. I know it's not going to be something you want to do, but we all got to do a little bit of work that week because technically Thanksgiving week is still a week that they count in the schedule of Navarro classes. It's a 16-week class, and you don't include Thanksgiving, it's only 15 weeks. So we've got to do a little bit of work. So today we're going to start on the next chapter, which is called the restless oceans. And so this is basically going to be about movement within the ocean, ocean currents, ocean waves, basic things like that. It's not going to be too bad. It's only 48 slides. So just like we finished the last chapter in 2 days, we'll be able to finish this one in 2 days and we'll be done with that. So yeah, we have gotten a little bit behind on the tests because I don't want to smash them together too much, but yeah, this test for these two chapters will be the day we get back from the Thanksgiving break, and those homeworks are due then. So know that I'm still recording the videos and putting them up on Canvas. So if you need to go back and recover something or take a look at things, they will be there. And make sure you're using your book to help you out through the homeworks. You should be able to find most of the answers fairly easily in the book. And if you don't, send me an email. Let me know, and I will either change the question or figure out where to find it in the book. So, starting off with ocean currents, basically they're going to give you the definition of ocean currents. They are masses of water that flow from one place to another. That's what a current is. It flows in a certain direction. We have two different types of currents. We have surface currents and deep currents. So surface currents develop from friction between wind and the ocean surface. Surface currents are pretty much exclusively from wind. We do get tides that move in and out. Tides don't necessarily affect the surface currents that much, though. Mostly it's which direction the wind is blowing. That's actually going to dictate where your water is moving. And because of surface currents and because of heating, there's actually a lot of reasons that kind of go into this, which we'll go through in the PowerPoint. We have huge, slowly moving gyres. And what a gyre is basically like a rotation, a full circle rotation of currents that goes throughout the ocean. They do change sometimes, but in general, if you kind of break it down into a big, large scale thing, you can see one constant gyre cycle of how the ocean water kind of recycles itself from warm to cold, from top to bottom. So they're going to start off here with the Coriolis effect. We're all familiar with the Coriolis effect in, it's going to sound silly, but in toilets in Australia. That's always been the U.S.'s example of the Coriolis effect, which is actually, I mean, y'all have heard that, right? Like, no? Yeah, she's. You didn't hear about the toilets in Australia? They never use that. Maybe that's a good thing because while water in the southern hemisphere does go down the drain in the opposite way, I believe ours goes clockwise, and in the southern hemisphere theirs goes counterclockwise. Although that might be, I don't know. I'll have to think about it. It actually, yeah, it deflects to the right in the northern hemisphere, so that would be clockwise, and then to the left in the southern hemisphere, counterclockwise. Um, the Coriolis effect is more than that, and in general, this is going to sound crazy. Toilets don't do that because of the Coriolis effect. They do that because we designed them to do that, because swirling is better to flush everything away than just going straight down. Um, but yes, you can see this more accurately in hurricanes. Hurricanes in the northern hemisphere spin a certain direction. Hurricanes in the southern hemisphere spin a different direction. And you have almost no hurricanes that cross over the equator from southern hemisphere to northern or vice versa, because the spin is opposite there, and they tend to fall apart afterwards. There are some that do that and kind of stay alive for a little while, but in general, you don't see a lot of crossover of hurricanes from northern to southern hemispheres. So the Coriolis effect helps deflect surface currents. It helps kind of guide the four main currents that we have that exist generally with each gyre that we have. Gyre is a weird word, but I'm going to have to say it a lot in the next couple slides. So we have 5 main gyres, and you can see that they correspond to different parts of our major oceans. We have the North Pacific Gyre, the South Pacific Gyre, the North Atlantic Gyre, the South Atlantic Gyre, and then the Indian Ocean Gyre. The other oceans that we have, which would be the Arctic Ocean and the Antarctic, the Southern Ocean, don't really have enough volume and don't really have a consistent setup to have their own special little gyre. And so it's just the 3 major oceans that we have, North and South Pacific, North and South Atlantic, and then Indian. And these are related to how the wind blows. And so with the direction the wind blows helps affect your gyres. And so here is an example of your gyres. The red arrows are going to dictate your warm water and where your warm water is traveling. Usually warm water is going to travel along the surface. The blue arrows are going to dictate where your cold water is traveling, generally along the ocean floor at the bottom of the ocean. So you can see in general, and I don't believe there's any exceptions here, all of your red arrows start at the equator. They're going to travel from west to east on the equator, which kind of matches up with the rotation of the Earth. And so they're all blowing west to east. You do have one arrow kind of going back in between over here. But in general, at the equator, all the winds and all the surface currents are blowing west to east at the equator. And then because they're at the equator, what's their temperature going to be for your surface waters at the equator? Yeah, you're going to have a higher temperature. You get more sunlight. These are your tropical and high heat areas. And so your waters get warmed up there, but they can't just stay there forever. And so you can see all of the surface waters at the equator eventually make a curve either north or south, and they begin their journey to the pole. So here in the Gulf and around Texas and the southeast of the United States, we hear about the Gulf Stream a lot. The Gulf Stream affects our weather quite a bit. And you can see the Gulf Stream in action. Warm waters come up from the equator, flow either into the Gulf of Mexico or further up the coast, bringing us usually warm weather and warm rains. And so they're going to continue to go up north all the way until they get close to the Arctic Circle, up here near Greenland. At that point, what's going to happen to the warm waters once they get near the poles, temperature-wise? Yeah, they're going to cool down. They no longer get as much sunlight. You're getting into the very cold areas of the Earth, and so they're going to cool down. And density-wise, think about your density of your temperature change in your water. Hot things are going to rise, cold things are going to sink. So when they cool down, they're going to sink down to the ocean floor. And when they travel back towards the equator to replace the water that's leaving at the surface, they're going to travel down along the ocean floor until they get to the equator, where they're going to warm up again, rise up to the surface, and start this whole cycle again. And so you can see the different gyres that they have. They have the North Atlantic gyre, which comes up from the equator to the North Pole, cools down, sinks down to the bottom, and returns back to the equator. The South Atlantic gyre, which goes down south, cools down, sinks down, and then goes back up to the equator. You have Pacific gyres that do the same thing, go up, cool down near Alaska, come down all the way back to the equator, and the same thing down here in the South Pacific. And there's not a lot of Indian Ocean north of the equator, and so generally your Indian Ocean gyre is just the southern part of the ocean here, but it has that same kind of cycle. Warm water going south or north, sinking down when it cools down, and then traveling all the way back up to the equator to replace the water that's leaving there because of the gyre. So it's all this kind of circulation effect happening. Now, let's see. The importance of surface currents on climate. And there's a question about this in the homeworks for this chapter. So warm currents transfer heat from low latitudes into higher latitudes, kind of moderating the effect. Influence of cold currents is most pronounced in the tropics during summer months. In the middle latitudes, that brings a chill to the air and increased aridity. So aridity is going to be the opposite of humidity. It increases your dry air and your cold air. When we get kind of that hot, moist heat from the Gulf, it's usually bringing in hot, I don't know, your hot air can hold more moisture. Your cold air can't hold as much moisture. So the colder the air, generally, the more dry it is, in a way. So how does the Coriolis effect influence ocean currents? It deflects the surface currents, causing them to move to the right in the northern hemisphere, to the left in the southern hemisphere. And then they're going to talk about coastal upwelling. So upwelling is actually very, very important. It's the rising of this cold, deep water to replace warm surface water. Wind-induced vertical movement, which kind of needs a little bit of explanation. Basically, when you have water leave some area of the ocean, like a surface current blows it away, you have to have something to replace that water. You're not just going to have like a dip in the ocean or a hole in the ocean. And so if we go back here, yes. When you have wind blowing these waters away from the coast here in Africa and away from the coast here in Southern America, the wind's blowing the water away. It's blowing it further to the west. You have to have something to replace that water. It's not just going to like blow a hole in the ocean. And so what replaces that water that's blowing away at the surface? The water from beneath. It's going to come up to replace that water at the surface, and it's going to be nice and cold. And so I don't remember exactly where it is, but somewhere, I believe in Peru or Chile, there is the world's largest outdoor swimming pool, and it's right on the beach. It's literally like you could step out of the swimming pool and just be on the beach. And as like a Texan, your brain's like, why would you build a swimming pool on the beach? Like, you have the beach there. There's all the water that you want. What do you need the pool for? And the truth is, on this west coast right here, the water's too cold. It's just extremely cold water because of that upwelling. It's come up from the poles, and here it has nowhere else to go. It has to come up to replace the warm water that's moving to the west. And so you have very, very cold waters along the coast of Peru and Chile here. And that, it's a nice vacation area, and it's nice to walk along the beach because you're still, at the equator. It's nice temperatures in the air, but the water is very uncomfortably cold. And so to kind of placate the tourists, they built a giant swimming pool right on the beach to kind of counteract the very cold waters that you have in the ocean. So you can still swim and enjoy yourself and enjoy the weather, but you don't have to be freezing cold in the waters there. So that is all due to upwelling. The wind kind of blows the water away. It brings up water from the bottom. Most characteristic along the west coast of different continents. So I showed you the west coast of Africa and South America. Coastal winds combined with the Coriolis effect cause the water to move away from the shore from east to west, kind of blowing it away. So this is an example here. They have their temperature scale. What is this? Chlorophyll? No. This is not temperature. We're getting to the next part. So along with cold waters that get upwelled from the deep ocean surface, this actually brings um, a lot of minerals and a lot of, what's the term that I'm looking for? I guess just minerals is fine. It brings a lot of stuff that life needs and likes. And so often right off of these coasts that have upwelling, despite the very cold temperatures, you have a flourishing of animal life. So you can see this is a chlorophyll concentration. Chlorophyll, we're familiar with chlorophyll from plants. This is also going to be like from algae and microscopic organisms. And so you can see as you get really close to the coast here, you have a very high chlorophyll concentration. And that's because of all those minerals and nutrients being brought up. Nutrients is what I was looking for. Nutrients being brought up from the deep, cold ocean water. And the animals at the surface, the microscopic little animals and plants at the surface, take advantage of that, use those nutrients, and they kind of thrive. And so you have a high chlorophyll content there. Now, deep ocean circulation. So deep ocean circulation is a response to density differences. If you have cold water, it's going to sink. So they say that here, cold water is dense. Also, saltier water is going to be more dense. It's going to sink as well. So the saltier your water is, the colder it is, it's going to sink down. And we already kind of established that your density of the oceans in the last chapter, the density of the oceans at the equator is slightly lower because you have a lot of rain and moisture that's added to the surface ocean water here. If you think about it, these are like your tropical rainforest areas. They get an immense amount of rain. All of that rain is going to be just more and more fresh water that's added to the water column. And so you have a dip in salinity here that also makes it more buoyant and rise to the surface and stay warm. And so your warm waters stay at the surface, your cold waters are going to sink. Your warm waters are more likely to be less dense with salinity as well because they've had more fresh water added to them. So this is called thermohaline or haline circulation. The thermo part is obviously heat. Haline is referring to halite, the mineral salt. And so this is your heat and salt-induced circulation. That's what kind of drives these circulations is the density caused by your temperature change and caused by your salinity change. So most water in the deep ocean currents begins in high latitudes at the surface. A simple model of ocean circulation is your conveyor belt traveling from the Atlantic Ocean through the Indian and Pacific Oceans and back again. And basically what they're saying is your cold currents that flow along the bottom of the ocean have to come from somewhere. They don't just stay at the bottom forever. And so as they go up to the high latitudes, they're going to cool down, which is going to help them sink. And they're getting away from that freshwater input. So they're more likely to be high salinity. That's also going to help them sink. And then they're going to travel back towards the equator. And so here they show you the conveyor belt. We already saw the gyres, and the gyres are all kind of included here. You have a North Atlantic gyre, you have the South Atlantic gyre, but it kind of shows how they're all interconnected. The Indian gyre, North Pacific, South Pacific gyre, but it's not like a piece of water or a molecule of water that's in the North Atlantic. It's always going to stay in the North Atlantic. There's ways that it can travel kind of all over to different countries. And so you see, let's start off here at the equator. Your warm surface is flowing from west to east, as almost all of the waters at the equator does. So it's going to flow from west to east. At some point, it's going to start to head up towards the poles. At the poles, it cools down. It gets more salinity. It's going to sink down to the ocean bed underneath at the ocean bed. Is that right? It's early. I don't know why my brain's not working that great. But yeah, the floor of the ocean. It's going to sink down to the floor, come all the way down to where it joins with these cold waters that are kind of circulating around Antarctica. They can come back up and surface at the equator in the Indian Ocean. They can come back up and surface at like the west coast of North America or South America, and then begin that same journey. And so this kind of shows an interconnection between the gyres and how water can kind of flow to any part of the oceans on the earth. They're not just stuck in that same little cycle in the North Pacific or the South Pacific. They can go anywhere you want to. So I know there's a question about this map on the homework as well. So if you have any questions about this, let me know, and I will try to help you answer it. So shorelines are constantly being modified by many different things. Waves and storms obviously are going to change your shoreline. They're going to cause erosion. I don't know how old y'all were. Do y'all remember Sandy? Yeah, Hurricane Sandy. It hit like New Jersey, like messed up the boardwalk. It was a big deal, but it really did a lot of erosional damage to the shorelines up there. Sea level change can also obviously change your shoreline. New Orleans is kind of worried about that. They're right at sea level. If you haven't heard about Venice yet, have y'all heard about the problems in Venice? Venice is getting flooded now more often than ever. They're just like New Orleans, very, very close to sea level. In fact, probably more so. Venice is the city with the canals. And so literally the ocean is right there, all in their city, and they kind of built their city in the ocean. And so even just a little bit of sea level rise combined with local storms, they get flooded fairly often. You can see videos of like the water all the way up to like the doorstep of shops in Venice, and people walking around with no shoes and their pants rolled up. And so sea level change, even just a slight little bit, depending on what city you live in, can be a huge problem. Stream erosion and deposition. If you have your stream kind of change paths, fill it up with more sediment, the water's going to need a different place to go, and so that can kind of change where your flooding happens. Glaciation can either remove sea level, or if you have melting of glaciers, that can add to the sea level. Volcanic activity, tectonic forces, and human activity. The volcanic activity and tectonic forces changing the shoreline. When you have more plate tectonics going on, the idea is your crust is kind of swelled, and there's more activity. There's more mid-ocean ridges. It leaves less room in the ocean basins for the water to be there, and so your water level is generally higher in those times. I believe this is a picture of Sandy. So you can see the beach here, all these houses on the beach, and they just kind of got tossed about. The foundation that they were built on, which was mostly just sand, which isn't smart, it kind of got eroded away all in one fell swoop for Sandy. Don't worry too much about them. They could afford beach houses to begin with, but it was a pretty bad storm, and they were not prepared for it. Not too often a hurricane of that size and magnitude hits that far north on the eastern seaboard, but it did this time. In fact, I believe, I might be wrong, but I think I'm right. Let's see. The book for next time. Yeah. The cover of the book for next time, probably depending on which version you get. The cover of the book from next time has a picture of a roller coaster, like in the ocean. That's from Sandy. They have a boardwalk there, and they had a roller coaster, and the boardwalk got destroyed, and the roller coaster, I don't know if it was in the ocean or it got like washed out into the ocean, but summer was not the same for them that year. So let's see. Now let's talk about waves. There's a lot of study that goes into different waves. There's a couple things that we can talk about, and this is another question in the homeworks. So there's two different major parts of a wave. You have your crest and your trough. The crest is like the peak of the wave. The trough is the anti-peak, the low part of the wave in between the two crests. there's two different measurements you can make on your crest and your trough. You can have your wave height, and that goes from the lowest part of the trough to the highest part of the crest. That is your wave height. And then you also have your wavelength, which stretches from crest to crest. To be fair, you can measure wavelength from any point. You can measure wavelength from trough to trough. You can measure wavelength from zero crossing to zero crossing. It just depends on how you're doing it. The easiest is probably crest to crest. But you should get the same length as long as you're using the same 2 points in subsequent cycles. The other thing I'd like to point out, which is also asked about, what these circles are the motion of like a single particle in the water. So like if you have a piece of sediment or even just a single water molecule, what is that water molecule going to do? Or I guess if these are big enough, if you're a person, what are you going to do as these waves are hitting you and kind of washing over you? So if the waves are traveling this way, you have a circular movement like this. So at the surface, you're going to go the direction of the wave. Obviously, the waves are going to push you that way, or surfboards wouldn't work. But below the surface, you're not always going to be headed that direction. There has to be some sort of water replacement there. Otherwise, the waves that are headed towards the shore would just always go up on the shore and they'd never go back. And so as at the surface, you're going with the direction of the wave. If you get below the surface, it's going to pull you back underneath and you're going to head the opposite direction of the wave. These circles are large and exaggerated at the surface. The further down you go, they get smaller and smaller and smaller. So if I'm like a little piece of soil suspended in the water down here, I'm just going to be making little tiny circles, back and forth, back and forth. Now, at a certain point, you get below the area where the wind and waves can affect you. You don't really feel that push and pull of the water anymore. That's basically considered below the, I want to say it's called the storm line. We might see that in the next chapter. But below this line, you're not going to feel the waves moving above you. Above the line, you will feel them slightly, and then as you get more towards the surface, you'll feel them more and more and more. But below the line, you're just going to be a steady molecule of water or sediment or whatever you happen to be, not really moving back and forth or up and down. Oh, and they actually give you a distance for that. So half of the wavelength. So if your wavelength is 10 feet, 5 feet down, you should not really feel the waves pushing and pulling on you anymore. That's the general breakdown of that. So they talk about wave height. Wave height is the distance between the deepest part of the trough and the peak of the crest. Wavelength is a horizontal distance between successive crests, or you can do troughs, like I said. Crests are probably the easiest to do. So pick a wave peak, measure to the next wave peak, and that is your crest. So wave period is how long it takes for the waves to pass. Sometimes the waves come very quickly. Sometimes it's several extra seconds in between waves. It depends on how hard the wind's blowing and kind of how big they are. So let's see. They're showing you wave motion here. This is actually kind of helpful. It illustrates what's happening to a boat that's riding along on the waves. And so you see this at the surface. It also happens below the surface. As the wave comes up behind the boat's going to kind of go back into the wave and travel up it. So you can see that back into the wave, travel up motion. At the peak of the wave's going to push the boat forward. And so you see that start to happen. And then as it goes down the other side of the wave, it's going to kind of go back to that original position that it was in. So it completes this nice circle as the wave comes up, and then it falls back down the back side of the wave. And isn't really pushed too far forward as the wave passes underneath it. This is also the kind of principle that allows surfers to get out into the waves. I don't know why surfers are always on the waves. It's a good example. But if the waves are always pushing you in towards the shore, how do the surfers get out there to ride a wave anyways? You in order to stay moving along with the wave, you almost kind of have to be on the peak or on this downward slope here. If you go over the top of the wave or underneath the wave, it's not really going to move you all that much, and you're still able to paddle yourself further out. So as the wave travels, the water passes energy in a circular orbital motion, and that's kind of always what happens. Now, we do have a couple other terms. Wind speed is going to affect how large your waves are, how fast they travel. Fetch is a new term. That is the distance the winds traveled to blow that wave. Sometimes the wind didn't travel very far. Sometimes the wind traveled from like a different continent or a different part of the world. That's going to affect how regular your waves are, and their spacing and their size. You can get kind of like a brief, let me think. You can get kind of like a brief sequence of waves because you get a really strong gust. But if you have an entire air mass that has been moving for hundreds of miles, you're going to get lots and lots of waves that just come over and over and over again and don't really have any let up. So fetch is kind of important to the overall wave cycle in a way. So what do we have here? Waves are unaffected by depth until they approach the shore. So yes, out in the deep ocean, when they're not really interacting with the ocean bottom, they're just going to be whatever the wind instructs them to be. Once they get to the shore and your shoreline kind of comes above this half of the wavelength distance, now the motion of your waves are interacting with the shore, and that energy has less room to operate. And so as you get closer and closer to the shore and the energy has less and less room to operate, your wave kind of gets pushed up above the normal surface. At some point, it will crest, and then it's surfing time. That's always what you want if you're on a boogie board, or even if you're just trying to enjoy the beach. No one wants to go to the beach and not have waves. If you didn't want waves, you should have gone to a lake. The beach is all about the waves, at least getting your feet in the waves. So know that when you have the waves come up and you get the nice crest or the nice like whitewater peak here, that's because the bottom of the beach is essentially pushing that energy up, and it no longer stays at the normal ocean surface. It has to come up above that. The bottom is slowing down due to friction as the top of the wave kind of speeds up. And that's why it kind of crashes over itself. So waves begin to feel the bottom at a water depth equal to the wave base. Slightly faster waves further out to sea catch up and decrease the wavelength, which causes the wave to grow steadily higher. When the wave is too steep to support itself, the wavefront collapses or breaks, which is where you get your surf. And surf is turbulent water created by the breaking waves. So surfers actually surf the surf. That is a geologic term. We made it, not them. I don't know who made it. Maybe they made it. Beaches. This is actually something that we have had hidden from us for a long time. Know that beaches, natural beaches at least, are made by whatever happens to be there. If there's just a bunch of animals living at the beach, if you have like a high biological content, your beach is mostly just going to be made up of shells. Imagine trying to walk on this with no flip-flops or something. It would be a nightmare, yeah. I went to, I know I've told y'all about this, but I went to Key West on a field trip for carbonates at OU. And some of the beaches, not all of them, but the beaches we went to, which are natural beaches because we're going for geological purposes, were terrible beaches. The rocks were very sharp and not comfortable. It's not a beach that you like slip the flip-flops off and walk around with the sand in between your toes. You almost need to have like the wet shoes on. But when we go to the beach for like vacation, you want those nice soft sandy beaches. Know that those sandy beaches don't really exist in too many places in nature. Oftentimes they're bringing in the sand and kind of laying it out on the beach to make it more more pleasurable to the tourists, so you will come back year after year. So they have the shelled beaches here. Where does it say this is? This is Florida's something island. Sandoval Island, possibly. Sanibel Island. I can't read it. It's too small. And then these are going to be black beaches, probably in Hawaii. Yes, I see the word Hawaii there. Hawaii has a bunch of volcanic rocks. They're all basaltic and dark colored. And so those rocks get weathered away by the beaches, and you have these nice black sand beaches. If you go to a white sand beach in Hawaii, that sand was probably brought in from somewhere, or kind of, I don't know if it can be manufactured there on the island, but there's not a lot of white rocks on Hawaii. It's literally an island full of black rocks. So white sand beaches aren't really going to be a thing that's natural there. Let's see. Now, rivers of sand. Sand in the surf zone moves roughly parallel to the shoreline. Wave energy causes sand to move perpendicular to the shoreline. Have y'all been to the beach, like down in Texas? And you go, like, your parents set up, like, the towel and your cooler and stuff, and then you go out into the beach, and you play in the beach for, like, 30 minutes or an hour, and then you come out of the beach, and I don't know how young y'all were, but you panic, because you look, and your parents aren't there. And you're like, my family's gone. Where have they gone? And then they're, like, way down the beach, and you're like, I didn't move that far down the beach. What happened there? That's the way the water pushes you. It does the same thing to the sand. It's constantly moving you down the beach, and you either have to get out and walk back, or constantly kind of moving against it to stay in the same place. But until the first time you've been in the beach, you're a little worried, because you get out and you're like, where's the towel? Where'd my parents go? And so that kind of happens to everybody the first time you go to the beach. So the sand in the surf zone moves roughly parallel to the shoreline. It's constantly going in a certain direction. Your wave energy causes sand to move perpendicular to the shoreline. And so that gives you a little bit of movement as the sand is kind of getting washed back and forth along the beach. And I think they'll show us this in an image in a second. And then we have wave refraction. Just like light waves or sound waves, they will kind of bend around certain objects. So bending of waves, as waves first touch the bottom of shallows, they are slowed, causing them to bend, and then the waves arrive parallel to the shore. So where are we at here? Yes, there we go. So here you have this kind of headland coming out, and you can see all the waves are set up like this. So you would think when this wave hits this part of the shore, it's actually going to be pushing that way quite a bit. But what happens is as it hits the headland, it's going to slow down this part, and the waves are going to kind of wrap around. So they're still going to hit relatively parallel to wherever the shore is. And we'll finish this up tomorrow. We're almost halfway. So everybody have a nice day.